Hello everybody, welcome back to the Professor's Du Bois channel. I am Professor Victoria and this is Professor Corey, and today we're going to be continuing on with thermochemistry and today talking about the manipulation of thermochemical equations.
So we've got a chemical equation written here, and we can tell by the delta H that it's an exothermic reaction. It's actually the combustion of methane, CH4 plus O2 going to CO2 and water. So we have a negative delta H, 802 kilojoules, and the negative tells us that it's exothermic. Now, what if we took the products and made them the reactants? So if we took the CO2 and the water and put them on the reactant side, and then from the original equation, the original reactants are now the products. We call this flipping the reaction. It kind of makes sense, like you almost just flip it so that the products are now the reactants. Well, take a look at the delta H. It's the same magnitude, opposite sign. So we can, if we draw this as a potential energy diagram, we could see like our reactants in our initial reaction, our reactants have more energy than our products. That's indicated in red. So we could calculate the delta H. We'd take the products, a small value, minus the reactant value, which was bigger, and it would be negative. But realize that if we went in the reverse direction, the magnitude of that delta H is the same. It's just the sign that changes.
So endothermic versus exothermic. All right, so it also scales these thermochemical equations, and the heat of reaction or the enthalpy change associated with it scales with the reaction. So if you have a certain amount that reacts and it gives off 802 kilojoules, then half that amount would be 401. So we can use this to manipulate these equations and say, okay, well, if 1 mole of methane reacting is 802, then half a mole of methane burning then is half that amount.
Again, we're kind of putting stoichiometry into a thermochemical equation.
Right?
The change of enthalpy depends on the state, so we have to be careful here. We've got two reactions that look very similar, except the second one, the water that was produced is in the liquid state as opposed to the gas state, and the delta H of those reactions are not the same. There's a difference in those of 88 kilojoules. So if you looked up in a textbook, the water in the gas state going to water in the liquid state, the delta H for that would be a negative 44 kilojoules per mole. And since we have two waters here, we can multiply that by 2, just like we said before, scales with the reaction. And there's our 88 kilojoule difference due to the change in state. So it's just kind of important. We're going to be looking up some of these values sometimes in like a table, and state is very important when it comes to thermochemistry.
All right, so you may have to manipulate equations in your studies and in your work. And so here's an example. We've got water, gas going to breaking apart into its elements of hydrogen and oxygen, and we have a delta H associated with that. That's endothermic. We have to put energy in to make that happen. If we flip it, we change the sign. So we just went from a positive to a negative down here. And it's the same magnitude. Remember the potential energy diagrams, it's just going in the reverse direction, and that change is the same. We can also scale it. We can multiply this by 2 if we want to know how much it is for 2 moles of hydrogen reacting with 1 mole of oxygen and producing water. We can just multiply that delta H. So this one, we multiplied this by 2.
And notice too that we multiplied everything by 2. So we went from 1/2 O2. If we multiply that by 2, we'd get 2 over 2 or 1 O2, and also the 2 H2Os here.
And our delta H. Here's a practice problem for you. So pause the video and give it a try. So we've provided you a delta H for a given reaction, and we want to know what the delta H is for the one down below. So you have to think about how is that reaction, how does that equation need to be manipulated to make it into the one that's down below.
And since they told the units as kilojoules per mole, you'll want to report your answer to kilojoules per mole as well.
All right, here we go. And there's your answer, positive 4,088 kilojoules.
Endothermic.
Endothermic. Yep, which makes sense since it was flipped.
All right, thanks for watching. That was quick, but manipulating equations, you can only describe it so long, and it really comes down to just practice with this. And I think the hardest part I find is when you get into fractions. It's sometimes hard with the fractions, but a little bit of practice goes a long way. So.
And this is going to be very important for our next topic, which is Hess's law. You need to be able to manipulate these equations to be able to do the next step.
Stay tuned for Hess's law.
Bye-bye.